slide we talked about or not? Let me click there and let me do this one down there, and that's basically our. Is it right or something else? Yes? This is the one, right? Is the last one?
Yes.
Yeah.
Thank you very much. Alright, so so far, if you recall what we have done so far, we have done the D-carabinose, sorry, D-ribose. I'm just writing the name only, okay? D-ribose, D-deoxy, I'm putting three-letter code, huh? Deoxy, ribose, and you already know they are pentoses. They are pentoses. And they are present, this is present in RNA, and this is present in DNA, right? The component of the DNA and RNA, all right? And the difference between these two is the C2 configuration. In the ribose have a D, and the C2 hydroxyl group on the right, and deoxyribose doesn't have a hydroxyl group, right, on the C2. Otherwise, C2 is a chiral center in C2 along with some others. Chiral center in ribose, D-ribose, but deoxyribose, C2 is not a chiral center. So that's the difference between these two. Make sure that you know, right, the structures and all those things. It is in the test one way or another. Huh? Hexoses. Hexoses, we talked about the GLC, right? It is GLC, D-gal, not in order, but D-gal, and D-men or mannose, right? Not the human man. Right, mannose. And these are the, you already know, these are the aldoses, right? Because they have LDH group, right? These are our aldoses. Alright. So these are our aldoses. And the one that we talked about is the ketoses. That is a D of fructose. D fructose. Tell me if you would okay, and you already practiced the structure and positive, okay? And this is the only one ketose. That's what we talked about, only ketones. And precursor for these guys, all of these, all five of them, is D-glyceroldehyde. That would be okay with it. D-glyceroldehyde. And the precursor of D-fructose is the dihydroxyacetone. It's acetone, right? So that's basically, definitely you should know that, and that's very important for the test as well, right? Then, and obviously D-fructose doesn't have a chirality, and if you look at the number of chiral centers, they all have a 4 of them at least, right? D-gal, D-glucose, D-gal, D-mannose have 4 chiral centers. D-fructose has only 3. Now the formula that I gave you, will extend that formula very soon, alright? And I already showed you the conversion of the ketoses, specifically between dihydroxyacetone. And then if you treat with those reactions, hydrocyanide, hydrolysis, and reaction with the sodium ammonia mixture, do the 3 times. And carbon number 3, DA has a carbon number 3, and if you do 3 times, it becomes 6, and that's basically you get the D-fructose. They're all these molecules from here, all of them is C6, H12, O6.
Professor Darren, I have a question really quick.
Yeah.
What does that word say that starts with an A?
Which one? This one?
Yeah.
Aldoses. A-L-D-O-S-T-S. Aldoses. They came from aldose. They're all aldoses because they have LDH group. But look at the molecular formula. All C6H12O6. Are they the same molecule? Answer is no. Answer is no, right? So the molecular formula doesn't tell you the structure of the molecule. So these are all structural stereoisomers. They're all called diastereomers and all those things, names are there. They're all stereodiastereomers. Alright? They're all C6H12O6. But the configuration, the arrangement of the groups, atoms and groups, hydroxyl group and hydrogen or CH2 groups are different. So that makes a different molecule. There are different properties also. So that's a one thing, right? Now, who can tell me quickly what's the relationship between D-gal and D-glucose? Relationship between D-glucose and D-gal. Who can tell me quickly? So that tells something about their structure as well. And the relationship between D-glucose and D-gal? Anyone?
Does it come in the fourth carbon with the hydroxyl configuration?
Say the word. You're right. Say the word.
That it is a 4-ephemer?
Yeah. That's a key word. Now, what's the difference between the glucose and the mannose? What's the relation between those two?
The two emperors.
You're right. 2 epimers, right. Right, yeah. Yeah, it's hard to pronounce, I know. But that's okay. 2 epimers. Yeah, that's the relationship. Alright, so that's our review. That's basically, we already did all of this. And D-glucose and D-fructose have very similarities in the carbon number 3, 4, 5, and 6. They have similarities, but 2 and 1, 1 and 2 are different. 1 and 2 are different. Alright, so let's get going to the next one then. Now, these molecules that I showed you, all of them, I did the line drawing, right? With the line drawing, but they don't exist in the line drawing. Line drawing is for our learning purpose. Those are called Fisher projection formula. So what do they exist in solution? They're all in soluble group. This is super hydroxyl groups. They're all common molecules. So what do they exist in solution? They exist in cyclic form. Cyclic form of aldoses, and ketoses. Cyclic form of the aldoses and ketoses. Alright? Cyclic form. So let's see the D-glucose. What kind of form does it exist? And please, by any means, please copy what I'm writing here. Because this is slide, if I give it to you and post it, that doesn't have anything else to say. Yes, Riley, what's up?
I'm sorry, but can you go back to the previous slide for 1 second?
Is it okay, Riley?
Yeah, thanks.
No, you're welcome. Alright, so once again, we got the molecular formula, we got the structure. That structure that we draw in hand, of course, in a piece of paper, of course, is the Fisher projection formula. So let's write the Fisher projection formula anyway. So Fisher projection formula of the D-glucose. I'll show you one, and then I'll extrapolate the fact to the rest. Because you already know the relationship between D-glucose, galactose, mannose, etc., right? So let's go carbon number 1, carbon number 2, 3, 4, 5, and last is 2 OH. Please write down. By all means, please write down exactly. That gives the practice of writing at the same time, and you'll see what's the changes occurring. If you do not, if you see it, you get lost because there's so many things will be there, so many changes will be there. This is me. Don't do everything. My cursor. All right. Okay. So OH. All right. Just write down a structure. If you write faster than me, great. Because you already know. So that's the glucose. D-glucose. We're writing the structure of D-glucose in a line drawing. But they don't exist in a line drawing, right? So what form do they exist? That's basically the question. And let's see whether we have answer or not. All right. Alright, so that's basically the glucose, D-glucose. Are you okay with it? If you have any question, please ask. That's a D-GLC. D-GLC. And I'm going to write the carbon number, not all of them. Carbon number 1, 2, carbon number 6, and that's our 5, and 4, 3, 4 in between. It's okay, right? Don't have to write all of them, if you write fine. So if we put the molecule in a format like this, so we are tilting the molecule on the right hand side, clockwise direction. Think about yourself. You have a molecule like this and tilt it in the clockwise direction. It will happen like this. It will happen C double bond O, this one, H will go there, that's a carbon number 1. And then we have this deadline, huh? Alright, alright. And then like this, and like this. Alright, have some. Yeah, please take this one, like this, and then like this. So the 6-membered ring. Please forget this one, this line, okay? I know, once you draw it here, and that's our CH2OH. That's the 6. Carbon number 6 carbon. So that's the carbon number 6. Alright? So that's a 6. Carbon number 6 is carbon number 1. And rest of them are in between. Alright? So you have like this, and you have like this. Okay? Look at the carbon number 2. So if you tilt the molecule towards the right hand side, the clockwise direction, hydroxyl group in the bottom. No doubt about it. Right? And therefore hydrogen is in the top. Alright? We are basically going to the cyclic form. Carbon number 3, hydroxyl group on the top, on the left hand side. That goes to the inside the ring, and hydrogen comes right here. Okay? Carbon number 4 is right hand side, so therefore it's the bottom. This and H. Carbon number 5. That's our carbon number 5, right? Hydroxyl group is right here. That's the hydroxyl group right here. And the hydrogen is always right here. Okay? Alright, that's very good. So this line, so if you do not write with me, you'll be confused what is this line for. This line is nothing. I cannot delete it from there. I don't know how that again. Alright. So now what will happen? You have a carbon number 1, 2, 3, and carbon number 4, 5, and 6. So what's so good? Oxygen has 2 pairs of lone pair. You remember, right? So this lone pair of electron from the oxygen, the hydroxyl group of the carbon number 5, can attack the carbonyl center from the top. It's attacking from the top. This. And therefore, the hydroxyl group will be, it will be a hydroxyl group like this. It will be O minus, and that H plus will join to O minus. So that something will happen. They are making cyclic compound, as you can see from there. Or, let's see if you have thousands of molecules, or a certain portion will attack this way, another certain portion will attack this way. We want the bottom, right here. We don't have any other color. Maybe I have, so you are attacking the bottom. So one is attacking the top, a certain portion, it will be 50-50. 50% of this molecule will attack this side, on the top, and 50% will attack from bottom. One is attacking to the top, hydroxyl group will go bottom. If you are attacking from the bottom, hydroxyl group will go to the top. So there will be 2 molecules. And they are like here. Right? So now you have a draw the structure again. So basically O, that's the O. And we have like this. Please tell me, and so just draw. This is a skeleton. If you have any questions, stop me anytime, okay? I'm just writing the skeleton. These are bonds. Alright? That's a carbon number 1. And let me other one. A similar kind. In fact, the same kind of things. This, and like this. Like this. Like this. Like this. Or one is doing better than this, but that's okay, right? So let's go on. Alright, so that's a carbon number 1. Now let's go to the hydroxyl groups, those atoms or groups. So let's assume the top one is attacking from the top. This lone pair attacking from the top. Remember, this is the nucleophilic center. Electrons are the nucleophile, therefore attacking the carbon. And hydroxyl group will go downwards. Right here, hydroxyl group will go to the downwards direction. Hydrogen stays as well. Alright?
Wait, so, are you saying that the lone pairs for in the hydroxide is attacking the carbon center?
Hydroxyl, the lone pair from the up. Yeah, that is correct. Yes, yes it is. Alright? So now, this one coming from the downside, and this one can, yes?
I have a question. So when you say attacking, you mean it's like trying to bond the carbon, which then creates
Yes.
cyclic motion?
Yes, cyclic motion and say take the hit away. Remember the nucleophilic center, nucleophile, when it attacks, it opens up the double bond. That's the theory. That's the basic principle we're applying here. Yeah? Yeah. Yeah.
Okay, but then, so then these next two molecules that you're showing, you are just showing what would happen if it attacks from the top versus the bottom.
Yes.
Okay.
That's the correct. So if we attack from the top, now hydroxyl group in the downward directions. If it attacks from the bottom, hydroxyl group in the upward direction. So that's the difference between the, remember, these hydroxyl groups are the one determining the configuration of the molecule. So definitely these two molecules are not the same. That's a carbon number 1. Remember, 2, 3, 4, 4, 2, 3, 4, and 6, nothing is happening. All there. So therefore, we put them back the same way exactly they had. So hydroxyl group right here. Hydroxyl group right there. Remember that's a carbon number 2, right? And hydrogen, of course, appropriate hydrogen. Fill it up. So carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 4 hydroxyl group on the bottom. No change. No change from 2 to 6. Alright? And 5 is the one making the cycle compound, of course. And CH2, OH, and H here. H there. And do the exactly same thing there. No change. Exactly, because you see, the only change is happening in the carbon number 1. Why carbon number 1? It's an aldehyde group. It is a triangular planar and is converting to tetrahedral mode. Tetrahedral. Alright, so rest of the things are remains the same. No change. No change in terms of the configuration. Configuration is the arrangement of atoms and groups, right? Configuration is the name, fancy name, or to tell the arrangement of the atoms or groups. Atoms or groups. Alright? Like this. No change. So that's our carbon number 6, carbon number 5, carbon number 4, carbon number 3, and carbon number 2. Alright? It's a 3, huh? Alright. Alright. So, few things. Of course, you know that these two molecules are not the same. You say, why? All the molecules so far we draw, their configurations are different based on the orientation of the hydroxyl group. Left, right, something like that. Here you have a top and bottom. One is the top, one is the bottom. So these are also some sort of isomers, right? These are called anomers. They have a name. I'm going to give the name and then I'm going to write the name, write the word. Huh? So these two are anomers. And this is when alpha hydroxyl group is the downward, it's called alpha D. D stands for the deoxy, GLC, glucose. It's alpha form. And this is a beta form. Beta D GLC. It's a name. It is another fancy name. And I'm not going to tell you, I'm going to tell you, but you don't know to write. The 6-member ring are known as, 6-member rings are known as, is known as pyranose. Pyranose. So this one is called alpha D glucopyranose. And this one is called beta D glucopyranose. But alpha D glucose, beta D glucose is perfectly fine. Perfectly fine.
Hey, excuse me. Can you spell it? Like, I don't know how to spell it. So
This
can
one?
you spell out what
This
it's
one?
supposed to be?
This one?
Yeah, at the ending, when you said Potanose, I don't know.
So you want to know the name too?
I just want to know how to spell it.
Yeah, I'm going to spell it. So alpha D gluco, GLUCO, pyranose, 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 pyran. Alpha D gluco, GLUCO, pyranose, PYRANOSE, nose, pyranose. Another one is called beta D glucopyranose. No problem, no problem. Alright, so alpha D glucose, these molecules are converting this to this, but their proportions are not 50-50. Usually it is a 40% solution, and this is 60%. Alright, so that's basically, if you have 100 molecules, 40 molecules should be like this, 60 molecules should be like this. Alright? And what do they call them? They have different configuration, different names. They are called anomers. 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 Mannose and anomers? Someone tell me. What's the difference between epimers and anomers? Epimers you already saw it. Epimers you already saw it, right? 2 epimers, 4 epimers, carbon number orientation of the hydroxyl group and hydrogen in carbon, respectively carbon. In this case, same molecule. It's a glucose. Same molecule, but carbon number 1 has a different configuration of those groups or atoms, groups and atoms, hydroxyl group and hydrogen. So same molecule. So epimers are different molecule, right? Anomers are the same molecule, but difference in configuration of a carbon number, at least only one carbon. In this case, carbon number 1. Carbon number 1. Everyone okay? The difference between epimers and anomers? Alright. So that goes to our D-glucose, and that's a very disease. Now, let's see, who can tell me quickly what will be the structure, what will be the cyclic structure of D-galactose? What is the structure of D-galactose? Can someone tell me quickly? Analyze the data. What is the structure of D-galactose? Alpha D-galactose, alpha beta D-galactose. What is the structure of alpha alpha D-galactose cyclic form? Anyone? Anyone? What is the structure of? You can tell. Now, what's the relationship between glucose and galactose? Tell me from this from there. What's the relationship between glucose and galactose? Anyone? Yes?
They're carbon 4 epimers.
Exactly. Exactly. So basically, and the rest of the carbon configuration are the same, right? So what you need to do, this is the carbon number 4. Hydroxyl group instead of downwards, upwards. If you put the hydroxyl group in upward, it will be alpha D galactose. Likewise, if you put this hydroxyl group in upward, right here, and the hydrogen downward, beta D galactose. That is correct. That is absolutely right. Yeah, yeah. The rest of the things are same. No change. Now,
Can you repeat what they have in common?
so glucose and galactose are 4 epimers. 4 epimers means the carbon number 4 configuration is different. In glucose, carbon number 4 has the hydroxyl group on the downward, and galactose has the hydroxyl group on the upward, right here, not down, and the hydrogen in the downwards. These are 4 epimers. So therefore, if you change this hydrogen to hydroxyl group and hydroxyl group to hydrogen, you get the beta D galactose. Likewise, you can get the alpha D galactose. Now, same gentleman, can you tell me how do you get the glucose and the cyclic structure of mannose?
Wait, when you said with the carbon 4, are you talking about the embers or the anonymous?
So relationship between glucose and galactose are the epimers, 4 epimers.
So with the E, not the A.
E.
Okay, thank you.
epimers, EI, yes. Now, can someone tell me what's the relation, how to draw the structure of alpha D mannose or and beta D mannose? Mannose.
Isn't the
Alpha.
second and third carbons change?
What the third? The relationship between mannose and glucose is the 2 epimer. So if you see the glucose, if you take this carbon, yes,
I'm in class.
yes. Okay, someone microphone is on, so someone talking to someone in the house. So that's fine. All right. So epimer, glucose and mannose, the 2 epimers. So glucose is hydroxyl group in the carbon downwards, and put the hydroxyl group upwards and hydrogen downwards is mannose. Rest of the things are same, exactly the same. So therefore, beta D mannose will be hydroxyl group on the carbon number 2 has hydroxyl group on the top, hydrogen in the bottom. And alpha will be same way. Alright? Now, how many in the this is a Fisher projection formula. Right? That's a Fisher, the name of the scientist, right? Fisher projection. That's a projecting, that's basically a projection. Right? A Fisher projection formula. Yes, Katie, what's up? This is a projection formula.
Just had a quick clarification that I want to make. So are you saying that for glucose it changes the hydroxyl group on 1 and then mannose changes it on carbon 2 and then
It's not changing. It's not changing. No, it's not changing. We are trying to draw the structure of alpha D mannose. What will be the structure of alpha D mannose? Easy way to do it, change the orientation of the hydroxyl group with carbon number 2. And here also carbon number 2. If you want to draw the structure of alpha D galactose, change the hydroxyl group in carbon number 4 up and hydrogen in the bottom. And beta, hydroxyl in the top, hydrogen in the bottom. Why? Because mannose, the galactose and glucose have a 4 epimers configurations. Different. Mannose is the difference in 2 epimers. Alright, so this is called Fisher projection formula. So what do you call this? They are not the same. This is the one they exist in solution, in reality. They don't exist like this. This is for learning. This is for reality. So what do you call that? This is our Haworth projection formula. Right? Haworth. Alright? Haworth is the name of the scientist. Haworth projection formula. Haworth projection formula. Projection formula. Right? So Fisher projection formula is a line drawing. Haworth projection formula is the real stuff. And that's a cyclic form of the glucose. Now, who can tell me in the Fisher projection formula how many chiral carbons are there? The Fisher projection formula. And how many chiral carbon in the Haworth projection formula? In the Haworth projection formula, how many chiral carbons? And Fisher projection formula, how many chiral carbon? Chiral carbon. Anyone?
Are there 5 in the, or there's 6 in the Fisher projection one, and then there's 5 in the Harvard projection one?
Oh, how do you get 6? How do you get 6?
Wait, or would there be the same amount?
Is the carbon number 1 chiral center? No. Is the carbon number 1 chiral center? Or no? You already eliminated 1. Is the carbon number 6 chiral center? Or no? Yes? It is 2 hydrogen. Carbon number 1 has a double bond, no chiral center. Carbon number 6 has 2 hydrogen, same thing. You have a 4 different groups of atoms. So chiral center is right here. 1, 2, 3, and 4. These are the only 2, 3, 4, and 5 are the chiral centers in Fisher projection formula. So there are 4 of them. How many chiral centers in Haworth projection formula? Just take one. Do the same thing. Take one. How many chiral centers in Haworth projection formula of glucose?
Will it be 5?
Yes. Excellent. Absolutely right. Why 5? The carbon number 1 has a double bond. Carbon number doesn't have a double bond anymore. It is 1 hydrogen, hydroxyl group. This side attached to oxygen, this side attached to the carbon. 4 different groups of atoms. So 1, 2, 3, 4, and 5. That's right. So 5 chiral centers. So glucose in the Fisher projection formula has 4 chiral centers, and in cyclic and Haworth projection formula it is a 5 cyclic 5 chiral carbons. Yeah, chiral centers. So it increases by 1. Because this one is triangular planar, so I wanted to tetrahedral. Alright, let's do the D-glucose, the fructose, similar way. Alright, so D-fructose, as you know, CH2, cyclic form, what is the cyclic form, right? Of the D-fructose. And we wrote the ketose, all of them. C, double bond O. Now the structure for fructose again. Good practice. Carbon number 1, 2, 3, 4, 5, and CH2 OH, carbon number 6. Alright? So OH, if you remember the similarity between the glucose and fructose, the 3, 4, 5, 6, they're all the same. Same concentration. Carbon number 3, 4, 5, and 6. Carbon number 1 and 2 are the one different. Like this. So that's our D-fructose. Alright? That's our D-fructose. That is okay, right? No question asked? Now, it's the same thing. Position this molecule in a way, you'll have a cyclic form such that hydroxyl group of the fifth carbon will attract this. That's what's going to happen. So let's say 1, and why attack this? Because this is a carbonyl center, nucleophilic center. 3, 4, 5, and 6. It's number, right? So project it in a way. Project it in a way. So carbonyl group is the molecule of clockwise direction. That's what we're doing. So you don't want to. CH2, OH, reverse the same, no change. Alright? Reverse the same. So 1 and 2. That's a 2 carbon 2. This, and do this. CH2, OH, that's a carbon number 6, carbon number 1, 2, 3, 4, and 5, carbon number 5. Let's put those groups. So C double bond O, CH2OH, no change here. Hydroxyl group on the left hand side, so it will go to the top. Left means it will go top with the cyclic form. Alright? Other one is the bottom, so it's the opposite side, it's on the right hand side, and therefore it will go to this. And carbon number 5, no change. Carbon number 5 is the one hydroxyl group is using for the nucleophilic attack. So this carbon has this hydroxyl group has 2 lone pairs, exactly the same way. It can attack this carbonyl center from the top, or it can attack from the bottom, either way. It cannot have a same time. So a population of molecule will attack on the top, lone pair. A population of molecule, another population of molecule will attack on the bottom. This will be 50-50 attack. This was a 40-60. Here also the 40-60 attack. Alright? Now, therefore it will have 2 different molecules. So carbon number 2 has a carbonyl center, will open up. It's a triangular planar, now it becomes tetrahedral. Exactly just like here. It's an aldehyde group, it's a keto group. So now you draw the skeleton. This, right, and like this. Okay, we'll use that one as the line piece. Alright, so it's a 5-member ring. It's a 6-member ring, a 5-member ring, and we'll put those groups. Yes. So that's the one skeleton, and carbon number 1 is right here, CH2OH. If you look at on the left hand side, that's the carbon number 1, right? That's the carbon number 1. Carbon number 2 opened up. Hydroxyl group is attacking from the top. Hydroxyl group will in the bottom. That's what we said, right? Attacking from the top. Hydroxyl group in the bottom. Carbon number 2. No change. A carbon of 3, no change. Just put the hydroxyl group right there, and hydrogen right there. Hydroxyl group right there. No change for those. H, and CH2, HO, CH2. Again, this way, right? You get some space. HO, CH2, CH2H. That's a carbon number 6. And hydrogen here. So that's one form. So one form of this one. Now the other form. There's another form right here. Maybe right here, so that you can see better, right? You can see this. So this is other little crowded. I need a little bit more here, space here. So let's say the second form, it looks like this. Second form is looking like a looking like this way. Let's say let's move a little bit up. This. All right. And this. All right. We'll use as a hydrogen. All right. Yeah, we'll use as a hydrogen. All right. So put those bonds like this, like this, like this, like this, like this. Right. So that's your carbon number 2. Okay, this is carbon number 2, carbon number 1, and 2. This carbon number 3, carbon number 4, and carbon number 5. Here also, carbon number 1 is CH2, OH. Carbon number 2, hydroxyl group going to the downwards, right? Oh, sorry. Oh, the upward direction. So now I have to change the whole thing. Obviously, I cannot do that here. Let's try right here. I have some space right here. All right. So we can compare. Let's say we will do it like this. Like this. It will be smaller size, but that's okay. This hydroxyl group in the upward, right? Because the hydroxyl group is the carbon number 2, and CH2 OH, CH2 OH. So that's the number 1. That's number 2. And put the rest of it like this, like this. So HO is carbon number 6, CH2, and okay. And then, oh, come on. Okay, hydroxyl group on the top, right? No change in the carbon number 3, 4, 5, 6. This, H, and H, and H. Right? So that's basically the 2 different forms. As you can see from there, P, so that's a carbon number 3, right? Carbon number 3, that's a carbon number 4. Carbon number 5 and carbon number 6. No change. Carbon number 3, 4, 5, 6, no change. 3, 4, 5, 6, no change. Only the carbon number 2 up and down. It is a double bond. Now it is a tetrahedral structure. Nitrogen converted to tetrahedral structure. And once again, names are the same. The hydroxyl group on the bottom is called alpha D fructose. Alpha D fructose. And how about this one? Beta, say upward, beta D fructose. Beta D fructose. There is another name. Someone asked me, I just spelled it. I can spell it here also. It has another name too. It's a 5-membered ring. It is called alpha D fructo pyranose. Sorry, puranose. Q. F for 5. F-U-R-O-N-O-S-E. Furanose. F-U-R-A-N-O-S-E. Furanose. Alpha D fructo. Furanose. Furan is 5. 5-membered ring. Furan. 5. Furanose. F-U-R-A-N-O-S. This is called beta D fructo furanose. Once again, the ratio is the same. 40% to 60% in solution, 40% to 60%. So they are also, what do they call? How do you call this? This is the presupposition formula. What do you call this? Anyone? What are these called? Yeah?
The Hallworth projection formula?
Yeah, so this is how presupposition formula, but what do they call? Epimers, anomers, stereoisomers, what do they call? NOMRs. So C2 NOMRs. So the glucose was C1 NOMRs and fructose is C2 NOMRs. That is correct. C2 NOMRs. Yeah. C2 NOMRs. Alright? So NOMRs, ANOMERS. NOMERS. So C2 NOMRs, the fructose, C1 NOMR, the glucose. So NOMR could be the same carbon, the same molecule, right? Same carbon, same molecule, two different configurations. Alpha D group, alpha D, alpha or beta. Could be alpha D glucose, alpha D fructose, etc. So these are the real structure of the molecule they present in solution. It's called cyclic form. So Fischer projection formula is line drawing. Howard projection formula is the cyclic form. Now, in the Fischer projection formula of fructose, how many chiral centers are there? And how many chiral centers in Howard projection formula of fructose? You can tell me quickly. How many chiral centers in Fischer projection formula of fructose? That's the one.
Is it 3?
Yeah. 3, 4, and 5. So absolutely right. 3, 4, and 5. So 3. And how many Fischer position? How many in a Howard position formula then?
4.
How many? 4. How many?
4.
4. It always increases by 1. It always increases by 1. So 3 converted to 4. And this is 4 chiral centers are converted to 5. That is correct. That is correct. Alright, any question about this cyclic forms? Any question about this? These are the real structure, by the way. So when we talk about the RNA DNA component towards the end of the semester, then I will show you at the time the D-ribose and deoxyribose, how they are present. They are not present in the Fischer position formula that I gave it to you. For the time being, it's okay. When we talk about those again, then I will show you again how they are present in the cyclic form. Exactly the same way, but only it will be only 5 carbon instead of 6 carbon for the exoses, C6H12. Alright? Any questions? You have any questions? Anyone has any questions? How the cyclic forms of aldoses and ketoses exist? Yeah? If not, this is the importance of the aldoses and ketoses. Please write it down. Very important. We talked about many of them. D-ribose is present in nucleotides that are present in the precursors of RNA. Therefore, they are present in RNA. Deoxyribose, D-deoxyribose is present in the nucleotides that are the precursor of DNA. So they are present in DNA component. Deoxyribose, D-deoxyribose. That's where the name came from. Deoxyribonucleic acid and ribonucleic acid. D-galactose, D-mannose, these are all aldoses, and D-fructose, ketose are metabolic fuels. So whenever we eat some carbohydrates or proteins, ultimately they will convert it to glucose, galactose. Usually glucose and galactose are very common, and fructose. And they will go inside the cell and start degrading into the glycolytic pathway to pyruvate, and ultimately to a TCA cycle, and ultimately to go to the electron transport chain to generate ATP. These are all metabolic fuels. Metabolism, we will talk about later. Metabolic fuels. D-fructose is D-mannose is also metabolic fuel, but it is present in certain kind of grains like malts. Malt grain. Alright? Sugars.
So that's it.
Yes?
It's a lot.
Always, huh? Alright. I'll start with this slide, but I'll put this slide anyway in the website, in the Blackboard, so you can see their importance, and we'll start from there from Monday. Alright, we didn't go further, did we? No, that's okay. Alright. That's fine. Okay. Anybody has a question? I'm here. Anything you have a question, okay? Yes?
So we're having office hours here at 12 to 1:15, correct, today?
Today, well, today is 1 to 15.
Okay, 1 to 2:15.
Yeah, every day. time if you have any question. If you have a question now, fine. If you have question there, please come on. Come to the side. Same blackboard, same time. That you are.
Yeah, I just sorry, go ahead.
No, you're good. Go ahead.
Oh no, I was about to ask like a really like a distant question. Don't worry about it. Go ahead.
Okay. On this slide that you already have up, Professor,
Yep.
I see the like 4 going to 5 and then the 3 going to 4 on the like fructose and glucose. What do those mean?
So meaning the 4 chiral centers are converting to 5 chiral centers in the cyclic form.
Okay. All right. Thank you.
Same thing here. If fructose, 3 chiral centers are converting to 4 chiral centers.
Okay. Thank you.
Anybody answer the question? Yes, I'm going to discuss this. Means this also writing will be gone.
I just wanted to, which I know that you went over some of the stuff, but I had questions on like past topics that we went over.
Okay.
So do you want me to say them now or like office hours? Because I'll be at office hours.
Office hours is the best.
Okay.
Come at the time. I'll be glad to
Okay.
go with you. Okay?
Is it in Blackboard? It's in Blackboard, right?
So yes, it's the same time. Just have something to write. Yes, come here and you'll fill.
Okay. Thank you.
Welcome. Anybody else has a question? If not, I'm going to move on to the. All right. All right. If anybody has a question, I'm still here. Okay, let me put the attendance in my grade sheet, and then you can ask question also. I'm still here. Okay. All right. I'm going to put the attendance right here. All right.